First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of Roy and Whisker.
Hello.
Hello.
That was a safe entry to
Yes, I hear she has edited the intro.
I have.
Excellent.
Although Roy is an expert.
I don't understand though. Why did you edit the intro the same week that I learned how to do PCB design and design my very own custom propeller board? Because now I'm like an expert and stuff, and you can change it back.
I don't know if I would say that yet, Whisker.
Oh, schooled.
Oh well.
All right. So last week we talked a bit about counter A, counter B, and we got into video generation on the block diagram, pages 20 and 21. I think you had wanted to say something else about that, Roy?
Yeah, last week we talked about the video generation being able to do VGA and NTSC, and I failed to mention that it can also be used for doing PAL video generation as well. It's all in the code, which way it goes.
And what's PAL?
It's the European standard equivalent to NTSC.
Ah, I see.
Now, isn't the main difference between PAL and NTSC mostly just how many frames per second?
Yeah, it's
some resolution stuff too. Maybe how many lines or something.
Yeah, it's 50 hertz instead of 60 hertz, and then PAL has a handful more lines, like 500 and something instead of 400 and something. So
they're not terribly different. They work the same. They're just, timed a little bit differently. And
right.
I see.
A bit more detail in PAL.
I see. Okay. And did we talk about INO output register, IO direction register?
Oh, yeah, we covered all that.
Okay. I think, yeah, because I know we talked about the lines going into the chip. Okay.
Right.
So system counter. That's our next line.
Right. So the system counter is just a 32-bit counter value that goes increments once per system clock. So whatever the system clock is set to, 80 megahertz or whatever you set it to, it will count one tick per clock cycle. And then all of the cogs can read that count value and save it or wait for X number of ticks to go by. And it's a way for them to actually be connected to some kind of real-time increment.
So system clocks differ based on crystals and the PLLs and which, like, say you're using RC fast or RC slow.
Right.
Oh.
Now, one of the things that to be aware of is if you aren't using a crystal, then the system clock, while it will go once per cycle, it won't be a reliable time frame because the RC fast will drift.
Right.
RC fast and slow will drift a little bit, and so you'll have, it'll go a little bit faster sometimes, a little bit slower sometimes, largely based on temperature, stuff like that.
So you know how before I had asked whether or not you could change the timing, like change the clock mid program, and we were talking about how that would save power and such. So then if you did that in your program, that would change the system clock?
Yeah, if you change the system clock speed, say from using a crystal to using RC fast instead, then the system counter will count slower. That is true.
I don't know if I like that then.
Well, it's important to know about, and if you know about it, then you can code around it appropriately.
Right. Okay.
And it's not a big deal most of the time. Usually when you want to slow down the clock to get into lower power mode, it's okay if the system counter goes slower. You'll account for it appropriately.
Okay.
And another thing to note is that all of the cogs will get the same value from the system counter at any given access of it. If they're at the same clock, they'll get the same value. Although that's not that super important.
Okay. I wonder how Well, okay. I'm going to skip that question because it's completely like it wouldn't even be used. Anyway, okay. Let's just skip that. Data bus.
Okay, so the next two lines go together. They're the address bus and the data bus, and that's how the cogs interface with the hub to get hub memory or do hub instructions.
Okay.
And so what they do is they'll set on the address bus, they'll set a value for what address, and then on the data bus, they'll either put a value there if they're writing or read the value back if they're reading. And it's important to note on the lower part of page 21, you see the little thing that looks like a hub spinning around, connecting to each of the cogs there.
That's those two lines?
Yeah, basically the connection between the hub and each cog that's moving around there.
Yeah.
That's where the data and address bus are, logically connecting from the cog to the hub.
Okay.
They take turns accessing the hub. So at any given time, only one cog is actually accessing either reading or writing to the hub. And they, like I said, they take turns. So, and it's a fixed amount of time each time around.
Okay, now give me 1 second. I wanted to clarify something. This address bus, you're mentioning addressing. Now, is that saying like can you explain what addressing is a little bit?
Yeah, that's tricky when you're first starting out because the addressing is not obvious to somebody who's not already a coder, but it's very, very, very important.
Okay. But what is it? Besides being really important.
It's in the hub there's 32K of RAM.
Yeah.
You understand that part.
Yep.
Well, each byte in that 32K has an address. And it's sequential from 0 to 32,767. And each byte, one after another, has a different address. So the address bus is saying which byte are you referring to when you want to read or write.
So it's a bit like street addresses. You go down a street and the addresses go up as you drive along the street, right?
Right.
Each house is one location in memory.
Okay.
Okay. So in here, most of these are, be they RAM, be they ROM, be they, devices that you can talk to, whatever. It's just bytes that can be accessed from your program.
And do you have to in your program, do you have to call those addresses, or is it just by writing your program, it knows where those addresses are?
Well, a lot of that we're going to get into later, but for spin, most of the time what you're going to be doing is just using a variable name, and that's an alias for a variable. But when you add an @ sign to the front of it, that becomes the pointer to that variable, which is actually the address. So when you add an @ symbol to the beginning of the same variable name that you've been using, the value isn't the value of the variable. The value is the address in which that variable is stored. It's called a pointer. Now, we'll get into that in a lot more detail in such a way that you really understand it much later on as we get to that point. But for today's thing, you're more looking at the hardware there just to understand how it works.
Okay.
So I don't want to spend too much time on that.
Sure.
Right. So when you issue a command to the hub that is going to access memory, reading or writing, you set up the address, and then the data bus will be either filled up with the value at that address if you're doing a read, and then the cog will be able to read that value, or the cog will put a value onto the data bus and that will get written out to the memory.
Okay. And because this is because the data bus and address bus are only from the hub, then multiple cogs can't read it at the same time.
Well, it's because of the way that the hub is set up to function,
Yeah.
it goes to each cog in turn
Right.
and allows that cog to issue a hub command at that time slice. And hub command includes reading and writing, and it also includes other things like starting up another cog or stopping another cog. And there's a
Okay.
few other more
So, for
advanced.
example, in one of the little things that you've done for the videos of your little LED project that you've been working on to learn your code,
Mm-hmm.
you've done a cog new command with an at stack.
Yep.
Okay, that's basically the hardware side of what that line does.
So cog new, for those who don't know, spawns off a new cog to do something.
You give it the name of a pub or a private. Can you do it with a pri too?
Yeah, you just give it the name of one of your functions in
Yeah,
your program.
and some a pointer to some memory space, and it
And that memory space, if you call it at stack or at buddy, would be stack buddy.
at
Well,
buddy.
it's just the
At
address of some space in memory.
Remember what I was saying? How
Okay.
when you put an at in front of it, you're not talking about the contents of the variable. You're talking about
This.
the address that it is at.
Okay.
Right.
Okay. All right.
We know that that's very hard to wrap your head around as a brand new programmer because
get that.
we had to learn this way back in the day, and that's a really sort of alien concept until you get it, and then it's just like, oh yeah.
Well, that's fine. It's like the individual commands are the rooms of the house, and the house's address is labeled at stack or at whatever. So that it may take your program to that house, but within that house you have different commands that you need to execute.
Sure.
Okay.
Next
Question.
next time use an ice cream metaphor,
Why?
just because they're awesome and I'm kind of hungry.
Ice cream cone is addressable.
We could do sports
cream
or cars
flavors
too.
Are
But
the program? Okay, stop distracting. Okay, so I have a question then, Roy. So you said that cogs can, obviously cogs, they address the hub memory. They cause things to be written. They take things from the hub memory, depending on what they need or whatever. They can spawn new cogs, etc. So what if one cog wants the hub memory to give every other cog like a byte or whatever, a program or something to run?
Well,
And when it and then when it goes there, that cog wants to also like tell the hub memory to write something to everybody. Like isn't that like
well, it doesn't quite work like that. What
Oh.
happens is that the hub is just sort of a container,
right, a
holding-
repository of
holding the
knowledge.
memory,
Right.
right?
Right.
That's the best way to think of it. So the cogs are actually doing any kind of work, and the cog will write if a cog wants to share a value with another cog,
Yep.
it will write it to hub memory in a predetermined address that both cogs know about ahead of time. So like if
Oh.
you have code running in cog 1 to write a value to a specific address, say address 0 right at the beginning, and then code in cog 2 is written to read that address and see what value is in there and react to it.
And in Spin, this is even simpler. You've already done it a few times. Like in your RGB experiments that you've been doing, you've got the R, the G, and the B variables in your var section up at the top of your program.
Mm-hmm.
Those are stored in hub memory. So when you spawn off with cognew a function that just sits there doing the PWM for your RGB values,
Pulse width
and,
modulation.
and you change that RG and B values in another function somewhere else, the PWM that you spawned off into its own cog sees those changes and applies them accordingly.
Okay.
So just by using, hub memory to store your global variables, you can get that sort of cog to cog communication going on
Mm-hmm.
because they're both using the same alias and they're using a global variable stored in hub memory.
Okay.
Yeah, just something to clarify here. We're going over this graph and it's rather complicated, and some of the details here are really only important when you're doing
PASM.
PASM
Mm-hmm.
PASM programming or more advanced programming. When you're using spin, it's all much easier because you just have a variable and you refer to the variable in your spin code, and even if the spin code is running in a different cog, it can see that variable because it knows it's in the same program,
Hmm.
and it's all sort of handled for you by the spin interpreter and the compiler when you run it, the prop
Sure.
tool compiler.
Sure.
So we're kind of covering some of this stuff just so you're aware of what's going on under the covers.
Right.
But I wouldn't get too hung up on the details for now because they're really not necessary for spin, which is what we're going to be doing for quite a while because you can do quite a lot in spin before you need to go to PASM.
One
Okay.
thing that can definitely be said about knowing what's under the covers is by knowing it, learning spin will be much easier because spin is very simple and it's designed to do what it does on that hardware. So if you understand that hardware, then how spin does what it does will
Mhm.
make so much more sense to you. So that's why we're more than happy to sort of start off here with the fundamentals of the hardware, the stuff that most people wouldn't necessarily pay too much attention to. But because we've done a lot of this stuff already, we know that the more you understand the platform, the easier it is to understand the high-level language.
Sure.
Right.
Sure. Okay. I just wanted to make sure with the hub and the cog communication that there wouldn't be conflict of interests, so to speak.
Right. There can be, but it's generally only in certain situations, and the propeller makes it a lot easier because of the way that it takes turn giving the cogs access to the hub.
Mm-hmm.
It makes it a little more difficult to have problems where two things are trying to access the same spot at the same time, which can happen on other processors that are multi-core.
Yeah,
Um,
it would be a good thing just to stop for a moment here and say that one of the things that Roy has heard and I've heard and I'm sure Addie may have heard as well is people who are used to doing multi-threaded programming in like C on a modern microprocessor, something like that. You tell them that the propeller can do 8 things at the same time, and the first thing that they almost always say is like, well, what about memory protection between the threads? And it's like, no, dude, that's not how this works. Because the hub takes turns going round and round and round, letting each of them have a chance to deal with memory. You don't have the problems of two threads accessing the same piece of memory at the same exact time.
Hmm.
So it may make some processes take a little bit longer because it does it that way, but it also makes developing for the platform a million times easier than it would be if it allowed them all to access it simultaneously.
Sure.
Now, there is, just to clarify, in more complex programs where you might be accessing multiple longs or multiple bytes of data
Mm-hmm.
in the hub, then you can run into similar problems that you run into with multi-threaded, because for each given time around, you can only read or write one memory location, one long at the most. So if your data structure has 3 longs, then it will take 3 times around before you've updated the whole thing. And so another cog needs to wait. And they have a mechanism for that. It's called the lock bits, which is, if you notice on page 20 in the
Mm-hmm. The
block diagram,
locks.
that's
Yeah.
in the hub. And so what you can do is you can issue a command to lock, and you're locking one of the 8 bits,
Okay.
and you basically have the 2 cogs that are trying to communicate with each other agree on what bit is the one they're going to work with.
Okay.
And you lock it, and then one cog can check that bit to see if it's set, and not do anything while it waits. So it does have a built-in mechanism to allow you to resolve the multi-threaded problems when you have a more
Uh,
advanced program.
okay, so
But
oh, go
most
ahead.
of the let me finish. So most of the time when you're dealing with this kind of stuff, though, you're only like you have one long and you write it and then another cog reads it. You won't have any kind of problems with that because of, like Whisker said, the round robin access stops you from having the normal multi-threaded problems.
Okay. So I'm gonna clarify, just like double check here. And so most commands that you will need when you're working with spin or what have you, with simple things, requires one long worth of memory to be accessed or transferred or what have you from the hub to the cog, cog to the hub. And so there's enough time when the hub comes to the cog for that one long to be dealt with.
Right.
Now, if there's like a command or a process that requires 3 longs to be accessed so that another cog doesn't change what you're dealing with, because since you only have enough time for one long to be accessed and you have 3 of them, you would need 3 hub cycles to take care of that command or what have you. And to prevent another cog from changing what you need to address, you would lock those bits.
Yeah, well, you would use a lock bit to flag to say, I'm going to change this value now, and the other cog
Cannot.
will read the log bit before it tries to do anything with those same values. And if it's set, it'll go, okay, well, I'll wait
Okay.
until it's not set. It's sort of
It's a flag,
a
like
cooperative way of both cogs communicating with each other when they have a more complex
It's like waiting your
mechanism.
turn,
Right.
but
it's
even
like
more so than the
throwing up
hubs.
the flag on your mailbox out front, so the mail guy knows to take the mail out that's in there.
Kind of.
Kind of.
Right. No, I get it. I get it. Okay. Well, that works then. That's helpful.
Yeah.
Okay.
And just to take it one step further, just so our listeners are aware, it's also true, even if it doesn't matter how many, it could be 3, it could be 2, it could be 100 longs. There are actually some cases where even one long might be a problem. For example, if the cog needs to read an address out of the hub memory and then change it and then write it back out,
Yeah.
then that might take a couple of cycles around of the hub. And so it might want to use the lock bits in that case also to stop somebody else from reading the incorrect value because it's about to change.
Right. So really, lock bits are used quite often.
They can be.
Well,
If you're going to do that sort of thing, usually what you're going to do is just avoid doing that kind of thing if you can at all help it.
Oh.
Like if you've got one cog working on writing into a variable, you're going to try to design your program in such a way so that nobody else needs to write into that variable. You might just have this guy is writing into one variable and his buddy over there is writing into a different variable, and then they're reading the variables that the other guy's writing into, and then you don't have this problem of them changing it while it's being written by the other guy.
Sure.
Right. You can write your code such that it's all coordinated, and then you don't have to worry about it. It's just that it's good to be aware of the feature being there so that you can use it in your more advanced programs down the line.
Right. Okay.
So the last couple things to cover in the diagram, if we have time, is you can see that there's on page 20, there's all these little boxes with arrows leading into the side of the gray box that says hub on it. And that's basically just all the stuff we covered in the past with all the clock configurations and whatnot.
Okay.
And the reason that that's all on the hub is because the hub actually has the configuration registers. And a register is just a special memory location that equals important data goes here.
Okay.
Right. And
for example, DIRA
Okay.
is just, a particular spot in memory. and it's a register. So when you write to that spot in memory, you actually change the direction of I/O pins on the chip.
Right.
Okay.
And that's an example of a cog register. The hub does have a couple of registers also, the main one being the configuration register, which configures the clock modes and all that. And we've already covered most of that stuff, but the way that that gets set is there is a command that you can issue on a cog during its time slice going around that circle. It can say, set the clock information now. And instead of reading or writing a memory address, it'll just write out data into the clock register, the clock configuration register for the, the crystal or PLL or RC fast, RC slow, all that stuff. And there's a few other commands that are like that, like we talked about cog new and cog stop and the lock
Those are all
bits.
registers.
Those are all special commands that occur when the hub and cog line up when it's going around. So if you try to issue that command and it's not lined up, it'll wait a little bit until the hub gets there and then it'll issue it.
Sure.
And
So there's like an internal queue, really.
It's a one deep queue at each cog, right? So each cog is waiting until the hub comes around and lets it do something.
It might be useful for you, Addie, to understand that it's a circuit on the inside.
Yeah.
So you've got a set of transistors that are a communication bus in between the hub and the cog. And when that round robin effect goes hub to cog 3, what it's doing is it's looking at the values of X number of bits across that thing that the cog has set.
Mm-hmm.
And that's the one deep that Roy just said, the one instruction deep.
Mm-hmm.
It can only see the one instruction that's being shown to it by the cog. And if it's of a particular type that says that the hub needs to do something, then it does something, right?
Right.
Okay.
And another thing to note, this is again a detail that's really only important in PASM, but if the hub is not on the cog at the moment that it wants to do that instruction that is one of the hub instructions, then the cog will stall and wait for the hub to get around to it.
Until the hub comes around and sees those literal like circuit bits that are on, it doesn't give that little electrical impulse back to the cog to say, okay, I've got that, continue on and do your thing.
So now if you're not using all your cogs, like say you're using one cogs 0 through 3, but not 4 through 7, and the hub gets there, does it just say, oh, there's nothing here, move on?
Right.
Okay.
Right. And so the hub always goes around to all 8 cogs, even if they're not doing anything. So it's a very deterministic amount of time. Each time it goes around, it takes the same amount of time.
Oh. So like if you only have one like things running in cog 0 and 1, you still have to wait for cog 2, cog 3, cog 4, cog 5, cog 6.
Because the hub is always going to go around and check those.
So you might as well use the cogs.
Well, yeah, or just it's just a thing to note that you'll have hub access once every X number of clocks, and it just works that way.
Okay.
And it's not going to get shorter or longer depending on what's running. It's the same amount of time every time.
Okay. Now you're going to be like, you're going to repeat that answer, I'm sure, a couple times here, but is there any way to halt the hub in one place? So say you're only using cog 0. Is there any way to only halt it there?
No. It always goes around all of them.
Okay. And there's no way to... So I guess in the same way you can't pause it.
Just like Whisker said, it's a circuit that's just constantly on. It's just constantly going around. And, the cogs, even when they're not doing anything, are on. They're just in a very low power state.
Okay.
They're just sitting there doing nothing, waiting to be told, hey, start up.
They're lonely.
Right? Kind of like you when you're sleeping. You're like, null, 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 null.
Thanks.
So we've covered this graph pretty extensively.
Yep.
Over the last couple episodes.
Cool. It's good timing because we're out of time.
I guess next week we'll go on to the next section in the manual.
Yes.
Awesome. And I hear rumors that we're going to be doing a little bit of stuff with the new Board of Education and some of the material that they're putting together for that as well in the near future here. So that'll be fun.
Correct.
Yep.
All right. That is it for us for this week. Thanks for listening. You can find this show every Tuesday on firstspin.tv. There's a little link on the side there, RSS or iTunes if you use that, where you can automatically download the show to your iPad, iPhone, computer, MP3
everything.
player, whatever you use to listen to your audio programs. So, yeah, that's it for us.
We'll see you next week.
Bye.
Bye.
Bye.